Hello everybody. I'm really happy to be with you from another side of the screen. Today I would like to tell you about some news in our Kinetics Neo software. And a main feature is a prediction based on climate temperature profile. And it's very important in our turbulent time. You know that our company produce instruments, and these instruments can measure the property of materials for given temperature program. But sometimes we would like to know something what could not be measured. For example, a degradation of coating or of plastics of some packages during several months or several years. In this case, we use our software, Kinetics Neo software, which could predict a property of any temperature at any temperature and any heating rate. The first feature is predictions for different climatic temperatures. Here, if you make a coating, for example, of gas or oil pipelines, then this coating has some lifetime. And this lifetime is different for cold climate and for hot climate. And the question, what is the lifetime of coating under different climatic conditions? We have some customers who produce some paints or some coatings for big bridges or buildings or big other constructions. And again, the question, what is the lifetime of this coating? Is it 5 years, 10 years, 20 years? And the customer comes and asks, what is the lifetime? He would like to know right now, not in 5 years, but right now. And this is again a question for Kinetics software. We have packaging. Packaging, we use it for storage. Sometimes we use plastics in agriculture, for example, for greenhouses. We use it for furniture. We use it in automotive industry. And unfortunately, we have plastic as a waste. And in any case, we would like to know what happens. What happens in 1 year, what happens in 2 years. And what happens if it is in cold climate or in hot climate. Then, for these questions, we use our feature, predictions for different climatic conditions. It could be used, firstly, for thermal aging, for packaging coating. It could be used for curing. Sometimes it happens outside, not only inside the building, for paints, for adhesives. It is very important for thermal stability, for storage and transportation of pharmaceutical and explosives. And it is important for ecology, for degradation, for example, the degradation of plastic waste. How it works? We just take a polymer, we put it in our laboratory, for example, under 4 TG Libra, make a couple of measurements. In this case, our longest measurement was with 0.1 K per minute, and it was about 5 days. We create kinetic model based on this measurement. And then we use this kinetic model for predictions for different profiles. For this purpose, we have map inside the software, and we have some points. The user should select a point. Each point on this map is a weather station. We have a little bit more than 100 different weather stations, and each weather station has their own ID, weather station ID. You can find it in internet and see what is the temperature and humidity right now in this moment. And for each weather station, we have inside the software the historical information about the temperature measured for last 30 years. So right now, the user can use this historical information for predictions. We have completely different profiles. For example, in USA or in Europe, it is cold in January and hot in July. In Australia, it's inverse. It is hot in January and cold in July. We have some climatic profiles where we have no any difference between January or July. For example, in Malaysia, it is the same temperature all over the year. Only the oscillation between nightly temperature, 24 hours, and a daily temperature, 32 degrees C. And we have sometimes very strange profiles, temperature profiles. For example, in India, it is cold in January and it is chill in July because of monsoons. For each profile, for each day, we have daily temperature and nightly temperature. It means maximum temperature and minimum temperature. And if we use temperature profile for several years, for example, for 30 years, then for this day of the year, we take 30 values for 30 years, exactly for this day of the year, and calculate the average. In this case, user can select the historical data only for 1 year, for 3 years, for 5, 10, or for 30 years. And of course, predictions could be done not only from the 1st of January, but from any day of the year. Here, with our polymer, we can put it in Australia for 10 years and see what happens. For this polymer, it happens mass loss, some degradation, with mass loss of 0.5%. And what happens in Canada? In Canada, for 10 years, a mass loss will be 0.01%. It's 50 times less. So degradation in Australia is 50 times intensive than in Canada. Another example, it's a very nice example from Claire Strasser from her new pharma book, 2020. Here we have calcium hydrogen phosphate dehydrate. Again, a measurement at different heating rate was done. We have kinetic model, and we use kinetic model for different profile. If this material will be stored in France for 2 years, then it has mass loss for 3%. If the same material will be stored in Indonesia, in Jakarta, again for 2 years, then the mass loss is 7%. So you can use this feature for prediction of different behavior of different process for a long time at different climatic profile. Next feature, temperature for adiabatic 24. Right now, we can make automatic search of initial temperature for given time to maximum rate and phi factor. It was today very nice shown from Gabi Kaiser what is time to maximum rate. And if we speak about chemical industry, then the mostly dangerous accidents in chemical industry is the reaction which goes out of control. So-called random reactions. And in order to avoid them, we must have some criterion which shows is it safe or not safe. And this criterion called temperature for adiabatic 24, sometimes TD24, and it means a temperature at which time to maximum rate is 24 hours. If we have this initial temperature, then during exothermal reaction under adiabatic conditions, we have increasing of a temperature, and then sometimes we have a maximum of a reaction and maximum of heat evolved. And the time to maximum rate is the time from the beginning to maximum of reaction rate. If initial temperature is higher, then reaction will be faster. Then we have time to maximum rate shorter, and then it's very dangerous. If initial temperature is lower, then we have very slow reaction. Then time to maximum rate will be long, and then we are on the safe side. Here it is very important for thermal safety for chemical process, firstly for pharmaceutical industry, nitration reactions, and for thermal stability of high energetic materials. Up to now, we have it only for arc in Protos. Right now, we have it for DSC and for other measurement method inside Kinetics software. How it works? Firstly, again, we have different measurement. We create kinetic model. Then we have a value of enthalpy from DSC. We go to the software, select predictions, select adiabatic 24, and put parameter. First parameter of enthalpy is just taken directly from DSC measurement as the area. Then we have specific heat. Usually it's about 2, you can change it. Phi factor, default value is 1, you can change it. Time to maximum rate for which we would like to calculate this temperature. We have 24 hours, but it could be changed. And then we just click calculate and get minus 2.8 hours for 24 hours for cyclopentadiene. So it means that this temperature is our safety criterion. And if you go to the literature, then for cyclopentadiene, it is written that at room temperature, a reaction goes during hours. For minus 20 degrees of C, it goes during days, and for long storage, it is recommended minus 80 degrees C. Last, very shortly, last new feature in our software, we can make a presentation of conversion rate as a sum of individual reaction peaks. Here we have measurement. We have, for example, 2 steps, and each step, each individual step, present their own peak. And here we can present each step as the individual peak for this reaction. And now, for example, we have 2 steps, 2 peaks, and 1 common curve, which is a sum of each. It is recommended in ICTAC kinetic recommendations for analysis of multi-step reactions, which is really a new article this year, 2020. It is used, it shows each peak separately, and you can see where your individual chemical reaction placed. And of course, you have a sum of this. It is used only for multi-step reaction. It is used for analysis, prediction, optimization. What is important, it is not a peak separation. For peak separation, we use as initial data in one curve. After that, we have mathematical peaks, for example, a Gaussian peaks for each peak. And after that, the peaks were independent. That was for peak separation. For peak separation, it is used for usually for melting of polymers or for some kind of things. Here we speak about chemical reaction. Initial data is not one curve, but set of curves. For initial data, here we have not a mathematical shape for each curve, not a Gauss, but we have a really chemical background. We have Arrhenius, we have first order reaction, nth order reaction, or maybe autocatalysis. It's really chemistry inside. And what is important here, the peaks are not independent. They are connected. For example, following reactions or competitive reactions. Thank you very much.